the topic for today, and there'll be all sorts of topics throughout the week, but the topic for today, this morning at least, is number sense, which is one of my favorite topics to think about. And really, I started thinking about it again. I had one of my former students who I taught as a sixth grader, who's now a senior, who came and visited Hillsdale as a prospective student. And he was talking to me about what the sixth graders and now the seniors at my old school still call the Great Greg Rampage of whatever year it was. And apparently this is now a thing like that they bring up. But it happened when we were sixth graders, and we were teaching the unit on percents. Okay, and I was just hammering home this formula. Part equals percent times whole, right? Over and over and over again. Part equals percent times whole. Part equals percent times whole. And we gave him this test, and there were a couple word problems at the end of this test. And one was about a $50 bike on sale, 20% off. What's the final price? And I guarantee you, I got answers that were $75. I got answers that were $2.50. And I was grading this test and just furious. And so I walked into class the next day, and I think I just let him. I don't remember this, but I must have just let him have it and said, when you finish any problem, you need to check your answer. And I better not see any of these kind of answers that I don't. This is what I'm picturing myself doing. I don't remember that happening, but it must have happened because they call it the Great Greg Rampage. And we did an entire week of every single time you got done with your answer, you went back and you checked it, and you made sure it made sense, and you had to write down on your homework, this is why this answer makes sense. And so you guys, I'm sure, have had similar experiences, right? This, just stupid stuff like, a 200-mile trip that you take in 4 hours that you do at 800 miles an hour, which, you just see these answers and you want to just slam your head against the whiteboard, right? You want to just, you're grading and you start drinking. And and from there, it's not a pretty sight. The rest of the evening is not a good mental or spiritual place for you to be in as a person. So not only does number sense matter for your kids' sake, it matters for your own sanity, right? But in all seriousness, right? Number sense is it's a tricky issue. It's not something that you're going to solve by 1 week of making your students check their answers. It's not something that we're going to solve in 90 minutes here, right? It's not something that you may even solve over the course of your entire teaching career. But I don't think just because we can't necessarily solve it here, that it's not worth bringing to our attention, and it's not worth making some progress, right? I think it's worthwhile, even if you're going from a level 1 number sense to maybe, level 2 or 2.5, right? Taking a kid from there to there is worth it, right? And it requires, so what I'm hoping to do is just bring up some thoughts, bring up some issues, spark maybe some discussion, and spark a little bit of, for you to give it some thought over the summer and go into the fall and say, I'm going to be intentional about this, because number sense doesn't happen. What I'm here, one of the main points I want to say about number sense is it's not something that either kids have or don't have. It's not something that you're born with. It's not something natural. Okay. Certainly, you're going to encounter students that are better at it than others, but number sense gets developed over the course of time and over the course of intentional teaching. And there's ways you can take, in whatever classroom you're in a 5th grade math classroom, you're in a 12th grade math classroom, you can take intentional steps to make sure number sense is a focal point of what you're doing in the classroom. So it's 100% not something that is it's not something that you just throw up your hands and say, well, my kids just don't have any number sense. Sure. Yeah. Okay. Good. So let's actually dig into this. So what do we define? How do we because it's a tricky thing to actually go and define, right? You know it when you see it, or you don't see it, right? More often when you don't see it, right? But what does it consist of? And this is probably one of the harder things for me to sit down and write a definition of what number sense is. So what I want to do, I want to actually try and take that question and give it some form, right? Allow us, right? That's a really abstract question. Obviously, I'm a Singapore math person, so like we progress from the concrete to the pictorial to the abstract, right? So I want to give it something formative, right? And the best way I can think of to do this is to give ourselves a math problem, right? So I'm going to give us a couple math problems. 2 math problems to think about first. Number 1. Okay, 2/3 minus 5/6 over 1/3 plus 2/9. All right, and 2. Letter is selected at random from each of the following words. Hillsdale College. What's the probability that we select one consonant and one vowel? All right? And I'm going to give you a few seconds for you to do one or both of these problems, or for some of you, attempt one or both of these problems. But while you're doing it, I want you to think about a simple question. I want you to think about what makes me good at solving this? Or, if you're struggling, what are the roadblocks that I'm having a hard time dealing with this? So, because I think that's actually going to give us a bit of an access into number sense, right? Is we're all sitting here, mathematicians or amateur mathematicians or whatever you want to call yourself, right? But what is it that makes us good at math or poor? So take a few seconds, solve one of these, or I'll even give some answers here, or maybe I won't. Maybe I'll see if someone can come up with some of the answers. But solve one of these, give them a shot, but ask yourself, what is it that makes me good at this problem? What is it that allows me to get the solution as opposed to not get the solution? Complex fractions in the summer. You gotta love it. You gotta love complex fractions in the summer. If y'all can remember your trick to complex fractions, that would be really helpful. Man. It's not an easy one. It's at least not a... I pull a letter from Hillsdale and I pull a letter from college. Right. I pull a letter from Hillsdale and then I pull a letter from college. So a letter is selected from each of the following words. Right. Pull one from Hillsdale and then pull one from college. So or the other way around. Just the probability. Like if I pull the S from Hillsdale and the E from college, that would be good. If I pull the H from Hillsdale and the C from college, that would not satisfy. Man, I love probability. It's my favorite. God, I love probability. It's the best thing in the world. All right, I'm going to stop you guys there. We can keep going, but hopefully you had a chance to think about, maybe you didn't take your solution to the end, but at least think about what it is that makes us good. Anyone willing to hazard an answer for this one? Yes? Negative 3/10 is correct. Negative 3/10 is correct. Anyone willing to hazard an answer for this one? 10 out of 21 is correct, yeah. 10 out of 21 is correct. You guys can work the rest of those on your own phone. But what I'm really looking for is what is it that allowed, those of you who got the right answers, what is it that allowed you to get those right answers? Those of you who didn't, what is it that you struggled with? What were some of the roadblocks that you had to overcome? Thoughts? What is it that makes us good? Yeah. Okay, so yeah, maybe I'll keep a list here. Right. Yeah, knowledge of the concepts and you have to know certain basic things. What a fraction is, what you should do first, right? The fact that this line is essentially a divide by. Yeah, divide by kind of thing. Yes. Yeah, factual fluency, right? Some kind of if any of you were here for some of my lectures to kindergarten through 6th grade teachers, oh man, I just beat them over the head with the stick of factual fluency, and that being one of the huge things you have to do in the lower grades. But yeah, the fact that we didn't have to stop and think what 3 times 2 was, or 2 times 2 if you made yourself a common denominator up there, right? The fact that we didn't actually have to, the fact that you know so intimately that 3 times 2 is 6, that you don't even have to think about what 3 times 2 is, right? If I say 8 plus 7, how many of you think 15? No, none of you think 15. You just associate 8 plus 7 is so intimately tied with 15 that you don't even have to think about it. You can focus your mental energy on other things, right? Because you're not intimidated or worried about facts. Really great point. Other thoughts? What really makes you good at this problem? Yeah. Good. Yeah. How many of you saw these problems and were like, yes, I'm ready to roll? Yeah. Excellent. Dig a little bit more into, not just the problem overall, what allowed you to make some progress on this problem? What allowed, yeah. Good, right? Right. Something that you have some kind of a you have some overall sense of what these symbols mean physically, right? You know that 2 over 3 is, 2 out of 3 parts, and you have this governing notion of what that physical might mean in the mathematical realm, where if I'm going to do 2 over 3 and 5 over 6, those aren't the same kind of thing, and I can't just straight subtract them across. Right? Good. Anyone, let's see, anyone do this to solve this one? Anyone multiply by 18 over 18? Solve this one? Turn it into 12 minus 15 over 6 plus 4. Is that it? Anyone do that? One person? Why'd you do that?
Well, a lot of my students are petrified of fractions. Every time they see a fraction, they freak out. So I tell them, if you don't like fractions, this is what you do.
Get rid of them, sure, right? So I'm with you on the process. What allows you to see that, or for those of you who didn't see it, what doesn't allow you to see it? Yeah.
I didn't see that because I'm looking. I have to do one thing and then the next thing. So I did the top and then the bottom.
Good.
That's the order that I did.
Right. So we're stuck in the step by step as opposed to some kind of a vision. Yeah, a vision for the end or the whole, right? If you know that at some point we're going to get rid, right? How many of you, when I put this problem up, could have told me that the answer is going to be some kind of a one number over another number? You all could have done that, yes? So you have immediately, as soon as I wrote the problem on the board, right? And now we're getting into a little bit into the realm of number sense. As soon as I wrote that problem on the board, you guys knew a few things about what the answer would look like, right? You knew that it would be something over something. How many of you could have figured out that the answer was going to be negative without doing any calculation? Yeah, someone tell me why it's going to be negative. Sure. Sure. The top's going to be less than 0, and the bottom's definitely going to be bigger than 0, right? If you've got a negative divided by a positive, it's going to be a negative. What about this one? What immediately, as soon as I put the problem up, did you guys already know about the answer? What'd you know? It's a fraction. Some kind of something between 0 and 1, right? Probabilities are always in between 0 and 1. We knew that immediately. If you got the answer 2.8, would you have been very, very upset? Yeah, all of you would have been, right? You have this vision for the end or the whole or what your answer looks like already. Good. Let's talk about this one for a sec. How did, those of you, someone who got the right answer, how'd you do it? How'd you do it? What'd you say? Sure. Good, right? So there's some element of counting. What else did you guys do? What else did we do? Okay, yeah. So you immediately had to make a creative step, right? There's not, this one you can go step by step and pull this one off. This one, there's no first step that lends itself to the answer. Right? There's no, okay, first I'm going to do this minus this, right? There has to be some sort of a creative step. There has to be some sort of a, where you say to yourself, okay, there's two ways of doing this. I could pull a consonant and a vowel, or a vowel and a consonant, and now I have, right, you can even, right, the way you start this one is to say, okay, there's vowel consonant probability plus consonant vowel probability. And now you can do whatever the fractions are, multiply them and add them. But what allows you, so dig a little bit deeper, don't be satisfied with that. What allows you to make that creative move? What is it that allows you to see that? Dig a little bit deeper. How does one see that? Or how would you take someone who doesn't see that and get them to see that without saying, here is the answer? Yeah?
Fundamental feeling or knowledge that what a probability is.
Sure.
Just that
Good. All right. Overall sense for what the physical meaning when we say probability, and also a vision for the end. Yeah, absolutely. What else? What makes you able to do this creative action? Yeah. Okay. Yeah, you've got this knowledge of concepts, right? You've got that background information. You're working with a certain set of tools in your toolbox, right? That's another way you can say this kind of thing. You have tools in your toolbox. I like that. Yeah.
Having done it many times before.
Okay. Yeah. Repetition, I think, is big. This is similar to some problems that you've seen in the past. Sure, you're able to recall and compare. Yeah.
It doesn't make a choice. Like, with my general knowledge of it, I said, okay, I'm going to deal with the idea of drawing a consonant from Hillsdale and a vowel from college, and you have to start with that, and then you have to be comfortable with the idea of, I know there's more to get to later.
Good. I'm going to press that a little bit because I think that's a really, really good point. Okay, so making some kind of a decision and running with it for a while. Pretend you make a decision and run with it for a while. Okay, got a couple questions. A, if you're on the right track, how do you know you're on the right track? And B, if you're not on the right track, how do you recognize you're not on the right track and switch things? Now we're really getting into the realm of number sense here, right? You can have those students in your mind who can't do one of those things, right? Who just, they pick a decision, because picking something and running with it is good, right? But there's got to be some checks along the way, because you have the student in your mind right now who picks something, runs with it, and just kind of barrels through, and whatever answer shows up is that answer, right? You have that student in mind, right? Perfect. Next problem. I picked something and I ran with it, and just, Okay, yeah. So how many of you guys, when you finished, looked back and said, that makes some sense, right? Especially this one, right? When you got 10 over 21, how did you check your answer? What did you say in your mind?
I went for the other combinations just to check, make sure it was one.
Really good, right? What's the probability that it's not a consonant, or what's the probability that you get two consonants or two vowels, and make sure that adds up to 11 over 21? Great. What's another way you could have just checked your answer?
First, make sure it's between 0 and 4.
Okay?
Yeah.
Make sure it goes with the prediction that we said at the very beginning. What else? Maybe just look at the letters and say, it's about 50% chance that I'm going to get a consonant and a vowel, right? There's about half consonants and half vowels. Makes sense that it's going to be about a half, right? Some kind of a ability to check your answer. Some kind of an ability to make sure things make sense. All right? Some kind of a way of making sure the track you chose was the right one, and if it isn't, being able to pick another track. I find that's actually often one of the hardest things for mathematicians. You can think about it in your own math, right? When you pick a track and you get to the end and you realize, I chose the wrong track, right? This is incorrect. You know it, have the ability to go back and figure out either where you went wrong, or that the track you chose at the very beginning was wrong. I think that's one of the hardest components of number sense, is the ability to go back and analyze that point. Okay, so I want to try to give us, these are really good ideas, and I think this is going to end up being how I'm going to define number sense, is by what, I'm going less for kind of this idea, just because knowledge of concepts, I think that's it's kind of in another framework, right? That's not really related to the number sense component. I think whoever said that is absolutely right, that you need the knowledge of concepts to be able to pull these off, right? If you've never seen the word probability, there's no way you're going to get that one right, no matter how much number sense you have, right? But I think that's the other realm, right? That's the conceptual knowledge realm. Obviously, it's a conceptual knowledge realm. I think number sense is more along the lines of some of these other things. So the things, when I was thinking about this, asking myself, what is it that makes me good at math? I came up with 3 things. And I think these are the kinds of things that are in those 3 things. But for me, the 3 things are 1. So this is how I'm going to define number sense. Is 1. So this component I think is huge. Some vision for the end in mind. Some ability to, before I start a problem, have a vision for what the answer is going to look like. Or at least what the answer should be around. Or at the very least having some beginning knowledge that about what even the form that an answer might take, or the an estimate of the answer, and it's not always something. Right? I'm not saying that I stop before every problem, because very few of you stopped, estimated, and then worked the problem. Right? None of you did that. I'm fairly confident. If you did, you're a better person than I am. But you jumped in headlong. But I guarantee you didn't jump in headlong without some subconscious idea of what that problem was going to look like in the end, of what that answer was going to look like in the end. And that, I think, is the number sense component. Okay? You began with that. 2. Right, so you can see kind of what I'm going here. Right? There's a beginning. Beginning of the problem, there's something that happens while you're doing the problem or within the problem, and then there's going to be something that I do at the very end, right? In the middle, okay, the number sense component, I think, is the ability is what I'm calling flexibility or playing around, or the ability to, it's this idea where you've got some kind of you have and I think there's some elements in here, right? There is the factual fluency. There is the sort of making a choice and running with it, and not being afraid to make a choice and run with it and say, I'm going to try this, right? There's the ability to, there's the comfort with being wrong, right? All of us are comfortable with being wrong because we think, okay, we learn things from being wrong, and we're able to kind of say, okay, well, that didn't really work. Let me try something else. Right? That took forever. Let's do it a little bit differently. Right? This is going to crush my soul. Let's find an easier path. Right? And we have the kind of flex. Right? It has to do with the conceptual knowledge. It has to do with the factual fluency. It has to kind of do with a little bit with the repetition. Right? It has to do with a lot of these things. But it's the ability to, while you're solving something, do things a little bit differently, change things up, look at the numbers in a little bit of a different way. I'm going to get to some examples of what I think this looks like. And we can come back to those in just a sec. But I think within the problem, it's the ability to be flexible. I think this is the hardest one to put your finger on. But 3, I think, is pretty easy. And I'm going to call it, what am I going to call that? Oh, yeah. Maybe I'm not going to call it that. I think, I should have thought of a better name than checking your answer. Let's call it, yeah, that's good. Some kind of a confirmation step. None of us, when we finish, if you think about it, if you really think about it, none of us, when we get an answer, are done at that point. We're not done at that point when we get the numbers of an answer. And even if you think, oh, I'm always done, you're not. You're checking it. Even if you're doing it subconsciously, you're comparing it to this, you're comparing, and actually almost all of us, if you really think about it, when you get the answer, you don't compare it to the steps that you did. You try to find another way of comparing it, another way of confirming it. Say, let's think about the problem, and right, when you got this negative here, right, hopefully what you did is you said, okay, I don't know if I was necessarily expecting that. Let's make sure I should be getting a negative. Right? And you did it a different way. You didn't say, well, let's make sure I did all my subtraction steps correctly. You said, let's look at the problem as a whole. Was my answer negative? Should my answer be negative? You're looking for a different way, right? And maybe I'm looking for, I don't know, some kind of creative confirmation or a variety of confirmation. Yeah?
When we were going through the problem for the probability one, I was thinking that flexibility in playing with the actual work involved in that. I think a lot of students may try to just memorize specifically that topic at the end on the board.
Right.
And multiplying and adding and stuff like that. So I think in that case, I was just thinking about those two parts of that problem, and then that confirmation would have to come through like a tree diagram or something.
Sure.
Or like what we're doing with that stuff.
Yeah. I think actually and the way that I work, I don't know if this is the way that you guys work a lot, but the way that I work is to use a formula actually as the confirmation of what I did as opposed to the process by which I do things. I don't know if too many of you work like that, but I'll often be doing a math problem and get done with it and go back and Google a formula for what I just did and see if it makes sense. See if what I did, things like that. But I think there's, none of us has, for any math problem, none of us has one way of doing it or thinking about it. We all are able to think about it through multiple pathways, right, of getting the same answer. And we use those multiple pathways to say, oh, yeah, this lines up perfectly, right? And there's two different scenarios, and in an and formula, or I guess it's an or formula, right? There's two different components to that formula, right? Oh, that's beautiful, that's beautiful, that's beautiful. And you're getting a little bit with that component, which I think is nice. But for me, this is what I'm defining as number sense. And I've said this to a few of you, I know already, but I think if we really think about it, this is what makes us good at what we do. And so, right, the big question being, how does one instill this, right? So the big question, right? Yeah. Okay, so I'm running with this definition of number sense, right? So, big question, right? How does one develop this in one's students, right? How does one get someone who doesn't do this to be able to do this, right? Good. I'm going to work, yes?
I would posit that the reason math teachers are comfortable being wrong is that predominantly they're right.
Yeah.
And we have some students for whom that is a different ratio.
That's a good point. Yeah, I think that's it. She said the reason why a lot of times we're comfortable being wrong is that we're often right. And so it's sort of a rarity, and that's not necessarily the case for most of our students. I think it's a really good point. I think the other reason why we're comfortable being wrong is we know that when we are wrong, we're able to pull ourselves out of that most of the time, right? Very few times in your lives probably have you been truly and utterly stumped by a math problem. Compare the subset of that to the subset of math problems you've done in your life, right? The fraction is minuscule, right? It's close to zero. Yes, close to zero. Number sense. I'm going to take these one by one. And try to give us both some things you can do. So what I want to try to do specifically is, I think there's a couple different ways you can access each one of these things. There are, I think, some specific things you can do in your classroom that are directly targeting one of these three things. There's also some things you can incorporate into your daily teaching habits that are, so I think in each one of these there's going to be a, right? There's going to be a direct way to address these things and an indirect way to address. And what I mean by that is just, I don't know. Pretend I think Mr. Wagner needs a haircut, right? There's a direct way I can address that. I can say, go get a haircut, right? Or I can do very indirect ways of addressing that, right? And sometimes the indirect ways are actually more effective than the direct ways, right? There's some very indirect ways I can tell him to get a haircut, or I can compliment Mr. Bourget on his hair. I can, reach over and pluck one of the stray hairs that he's got going on. I can. Yes. Oh no, they were not appropriate ways of doing this, but often the indirect ways are more effective. I think that's true in teaching as well, right? Often the things that we do directly to address something are good, but the things that we incorporate into our daily teaching habits are actually the things that make more of a difference, right? I think I found that to be true. Probably all of you do as well. So I'm going to try to give us some direct things we can practically do and some ways that maybe we incorporate into our teaching habits. I think as far as the three of these two are relatively, compared with this one, these two are relatively easy, or at least relatively easy to start working with your students on. So let's take this first one. Let's see. Let's do one. Vision. Some kind of a vision. Biggest practical, or biggest, let's do the indirect first, right? Best way of doing this is simply to make it a part of every problem. Make it a part of every problem. You can begin, so indirect. Just begin every problem by making predictions. It's an easy way of starting to get your kids thinking about this. Right? A lot of us jump directly into because here's the thing. None of you began this yourself by making predictions. Right? You just jumped right in, but that's not actually true. You had a prediction in the back of your mind this entire time. That's what we said, right? We had a vision for the end all along, right? So what we tend to do as mathematicians is jump right into the solving process, assuming that everyone has the same vision, or at least assuming that there is this vision that's going on in students' heads. And that's not true. The students don't have that. So you need to say in your mind, what is it about this problem that I implicitly understand, and make those questions real in front of your students, right? So asking this, right? Asking yourself. Right? Ask yourself, what do I implicitly understand? And those are the questions that you want to ask your students. Those are the things you want to make a reality. Okay? Good questions include, I wrote some things down. What's my answer going to be close to? Is it going to be bigger or less than 0? Is it going to be bigger or less than 1? Is it going to be bigger or less than 100? Bigger or less than 1,000,000? What is, even think of a simple problem. What is 843? How big is it? What's it close to? What is 194? How big is it? What's it close to? What is our answer going to be close to? What is addition? What does it mean to add? These are things that you don't even think about. I don't even think about. Give a guess for our answer. Why is it a good guess? Is there a better guess? Can we do, everyone write down a guess on your paper. Let's list them up here. Ask, why did you guess that? Why did you guess that? Why is it going to be bigger? It's all these why kinds of questions without even starting into the calculation, right? Tell your students, put their pencils down, hands in the air, look at me. Before we even do the problem, let's figure out some things that we can predict about what it's going to look like. Don't let them start jumping into calculation, or don't assume that they can. Right? This one, right? Is the numerator going to be greater or less than 0? Is the denominator going to be greater or less than 0? Is the answer going to be, the numerator going to be greater or less than 1? It's very difficult to get your kids to be able to estimate the answer to a problem like this. But if you were going to estimate it, just ask yourself, how would I do it? What do I know in the back of my mind? And ask your students those questions to start your lesson. Start your problem. Have them make predictions about what's going on before they even start. The only way for them to ever internalize that and make that something that they don't have to think about is to start by thinking about it. The only way you habituate something is you have to actually do it for a while. You have to think about doing it before you unconsciously do it. The way you learned to brush your teeth at the end of the night, most of you, hopefully, is your parents made you brush your teeth every day until now none of you think about it. It's part of your daily routine. You have to be intentional about not jumping into the solving step before you're doing the gaining the vision step. Yeah?
The part of this actually depends on what level of the teacher.
Uh-huh.
So, when kids in first doing first and second grade, questions they ask them, but they're going to ask later.
Right.
With algebra, we're going to infrequently calculations of this sort.
Sure.
And this doesn't apply. You have all sorts of variables involved.
Yeah. Yeah. So let's throw a calculus problem up here, right? You're standing at the edge of a river. You need to make it back to your campsite. All right. You can swim. Let's see. This distance is 3 miles. Big river. That distance is 4 miles. You can swim at 1 mile an hour, and you can walk at 2 miles an hour. All right? Calculus problem. What are some questions you could ask beforehand about this calculus problem without starting it? No calculation required.
What's the velocity of the river?
Okay, yeah. Percent of the problem says assume the river is not moving. What are some questions? This is a difficult exercise. Think about it, though. What are something you could ask your students about this? Okay, yeah. What's your answer going to, even just what is the answer going to look like? The answer is going to be a time and some kind of a distance that you want to hit that opposite shore. Some kind of a spot that you want to, all right, and now you're getting into where your variable goes. What else could you ask? What shape is the tent? That might be a good way to hook them in, but probably not entirely appropriate. Yes? Do we have a car? No.
We're camping. Car's back at the tent.
Good, right? What's the direct distance? Think about, you guys are doing a little bit more, you're already jumping into the solving stage. You guys are jumping into the, let's calculate square root, and this is going to be 5, right? You're jumping ahead. I'm saying before that. What questions can you ask? Even before. Questions can you ask? Okay, something like that, right? What's a longer distance? Do we want to swim longer, or do we want to walk longer? Why? Why shouldn't we just swim directly?
Not only do you know the answer is in the format of time, but what type of time or what's your goal?
Yeah. Even getting them to make a prediction about the answer. Is it going to take me longer or shorter than an hour? Longer, right? But now you follow that up with why. Okay? Why is it going to take you longer? And now that student who answered longer has to go and articulate why it's going to be longer. Right? And it's going to be longer because at the very least, I have to swim 3 direct miles, and I can only swim at 1 mile an hour. So my answer is going to have to be not just bigger than 1, but some kind of bigger than 3. What's my answer going to be less than? Or what's the absolute maximum my answer could be? 5. And why are you saying that? You could swim directly there, and it would take you 5 hours. So now guess what I've done before any calculations have happened? I've taken a complex calculus problem, right? You have to use the chain rule to solve this problem. You have to take the square root of 3 to solve this problem, right? What? You have to take the square root of 3 to solve this problem. All right, we'll do it. And we'll take the square root of 3, I guarantee. We'll take the square root of 3. You have to do both those things to solve it, but I've already done this. I know my answer within 2 hours, which is probably not that short of a time, but it's at least, you've eliminated at this point all the answers that you might get that are 13 hours or 21 minutes. I could do it. You've eliminated those things already with a few simple questions beforehand, right? Oftentimes we jump right into the calculation step. Stop before you do a problem. Doesn't matter if it's a calculus problem or an algebra problem or a second grade problem. You can ask the same kinds of questions before you start. It goes a long ways. Don't let your students jump into calculation without getting a vision for what's going on. The best way of, so there's your kind of direct, I guess maybe that's less indirect, but one way of doing it, okay? Incorporate that into your teaching habits. Make it not something that you jump into. And it's the easiest set of questions to ask once you get in the habit of it, because you can just do it every time. You can just say, what's a good guess for this answer? Right? And if they say, well, I don't know, which a lot of students will look at this problem and be like, I have no idea. Right? You hook them in by saying, is it bigger than 1? Why? Is it less than 10? Less than 1,000,000? Why? And they'll be like, well, we know that this is true. It's an obvious thing, but it starts to be less obvious. It starts to be able to ballpark an answer. Indirect way of doing it. Direct way of doing it. The best way to do this. Activity, what I mean by direct is an activity specifically designed to address this. It's challenging them to do mental calculation. Okay? And I don't mean mental calculation of problems like 138 plus 412, although that would be good. Right? I mean mental calculation of some of the problems that you're going to see in the upper school. I mean these problems. And I'll give you guys a few. Right? Here, let's see. Some of the ones I did. Some of the ones I thought. Okay. Let me just give you 4 examples. "30 seconds. Who can get this one? No writing. Mrs. Huffman. This is mental calculation. Who can get it? 30 seconds. Sorry. Mr. Wagner, what you got? No idea. Everyone think they've got an answer? All right. Oh, Mrs. Reagan. Close. Actually, I'm doubting myself. Someone type it into a computer. It's got to end in a 2. How about this? Think about, I'm less interested in the answer so much as what happened when you were doing that? What happened in your mind? What did you do? Okay, you broke it up into pieces, right? Yes. You broke it up into some pieces. Right? And you also gained yourself a little bit of vision for the end in mind, right? You said you got an order of magnitude that you expected the answer to be in, right? You knew it was going to be in the 10,000s-ish, right? Somewhere in that order of magnitude, though, right? You also knew that it was going to end in a 2, right? These kind of things, right? The more you practice mental calculation, the better. Okay, let's give a couple other ones here. How about this one? No calculations. Sine of 37 degrees. A little more than a half, sure, yeah. A little more than a half. Somewhere right around probably 0.5. I didn't even write the answers down to these. I was just coming up with them, right? But, again, what'd you do with that problem? You knew something. Some of you might have thought about a triangle, maybe, or at least something on the unit circle, right? Some of you thought about the graph, right? Where's 37 degrees, right? And again, if you think about not letting your students type sine of 37 into their calculators all the time, do let them type sine of 37 into your calculator because, you can't calculate it otherwise. But before they're able to do that, have them stop and make a prediction. Give them a few, even this is a great way to start your day. One problem. Just one that they have to think about in their heads and give yourself a guess. Best guess, it's a night off of homework. No. But best guess gets, whatever you want, right? Something like, I don't know. Square root of 91. Cube root of 91. Right? Most of your students are going to be able to say it's between 9 and 10, but force them to go a little bit, right? Actually get the closest guess that they can get, right? Maybe have them think about, maybe some of you guys are doing 9.5 times 9.5 in your heads. Maybe none of you are doing that. Whatever, right? Mental calculation. Have some form of it in your class at some point. Right? This is not a calculus thing. This is not an algebra thing. This is just the best way to specifically target that vision. Right? Some kind of mental calculation. Don't let them type everything in the calculator. Do let them type stuff in the calculator, but don't make them make predictions. Natural log of 19. Really fun one. All right. Anyways, you guys get the idea. Should have brought a calculator to actually give some answers. Should have played that game right here. We should have had a little challenge. That would have been fun. I'm regretting not doing that. All right. Anyways. Questions about some ways to do, any other ideas about some ways to really get at number 1 here? Any other ways that you guys are thinking about? A lot of 1 is going to be connected to 2, right? And actually also 3. You got a calculator? All right, everyone make a guess of the natural log of 19. Everyone make a guess. Hold on. Let me just write them. Everyone make a guess. Anyone willing to share their guess? 2.6. That's Stark. 3.2. 3.2. Who was that? Plankman? 3. Who was that? 3. Doubtful, but. Anyone else? Any other one? Natural log of 19. 1.1. All right, what do we got, Mr. Wagner?
2.9444389.
Nice, Mr. Rappaport, victorious. Nice. You win. Right. Okay, but something like that, right? It's nothing. And now, what would you follow up that question? What question would you follow up that exercise with? Why? Yeah. How'd you do it? What do you think about? What were you thinking about? And talk about it, right? Your kids are going to be really bad at this at the beginning. You're going to be really bad. Right? The only way for them to get better is for you to give them a shot at it. to talk about why things are the way they are. Do it. It's fun. This is one of the fun parts of teaching. You get to make fun of people who say answers like 11.8 for natural log of 19. Yes? Oh, I usually just have them write it down, and then sometimes I'll throw them up on the board, but everyone gets to write something down and circle it just so that they know. Sometimes your kids have no idea what's going on. I'll make a guess, and they'll win, and then you'll have to ask them why, and they'll be like, I have no idea. And then you'll say, no, you wrote that for a reason. Why did you write that? And actually, these kind of things. I don't really take the time to put everything on the board necessarily. Sometimes it makes more sense to put some things on the board. It doesn't need to be a long part. And actually doesn't need to be at the beginning, right? If you've got some calculation during your lesson, is better. If you can circle that in your lesson plans and be like, all right, when we get here, everyone's going to give it a guess. It's a better way to do it. All right? Incorporate it actually into the lesson. Everyone makes a prediction for this one. You can also do it in your homework, right? Just a short question on a worksheet that says, make a prediction for this. Say why. Really good thing to put on a homework assignment. Just at the beginning. Number 2, stuck, flexibility. It's a tough one. Oh, I shouldn't have erased that. We're going to do that problem and see how we have to take the square root of 3. Flexibility. I like to just call it playing around. Some thoughts about how to do this. Let's do direct first. There are some math games you can play that directly make them play around with numbers. There's no way you can play the game without being able to do this. Just a couple that I'll mention. Not necessarily games, but let's just do ways. I've got 2 things in here. So there's games, something else. So things like, I don't know if I've taught some of you guys this. Taught some of you guys crypto. I've taught a few of you math dice, which is fun. I guess I'll teach you just these real briefly. No, I won't. Yeah, I will. Yeah, because they're fun. Crypto, just something like give them 5 numbers, and then a 5th number or a 6th number. You got to rearrange the first 5 and make them equal the 6th one. Something like this. Like that. All sorts of solutions to these. Guaranteed. They have to mess around with numbers. They have to try a bunch of different facts. You don't have to play with 5 numbers if you're teaching 6th or 7th graders. You want to play with 4 numbers, 3 numbers even. They have to mess with facts. They have to try stuff. They have to think about different ways of doing things. You're really high students, you can ask them for 3 or 4 solutions, right? Or low students, even if they don't end up getting a solution, they've tried 7 or 8 different things. They've had to play around with the numbers. Most of the things you try are going to be wrong, right? This ability to be wrong, this comfort with being wrong, because there's other things to try. Right? Other things to try. Math dice is pretty easy. I'll roll, you can roll whatever you want. I like to roll 2 20-sided die and 4 either 6-sided or 10-sided die. So pretend I got 19 and 6, and then, 2, 3, 6, and 6. Multiply the first 2. Play with You can play with only 3 of these. You can play with whatever you want. Right? Multiply the first 2 is, what is that, 114? 114? 114. 114. All right? Try to get those 4 to any combinations to get as close as possible to 114. All right? And what you do is when you get something, they can call it out. So, for instance, the first thing I might say might be, I don't know, I could hear someone say 41. Just as you're trying things, you're calling out your answers that you're getting. And then someone could get closer, right? I don't know, someone say 42, or 103. So I'm saying I could say 41 if I'm thinking 6 times 6 plus 3 plus 2. All right. I could say 42 if I'm thinking 2 times 3 times 6 plus 6. I could say 75 if I'm thinking 6 times 6 times 2 plus 3. And if you can get, who can get closer? Someone call it a number. Yeah, call it out.
6 times 6 times.
Just call it the number. Just call it what you got.
110.
110. You use exponents if you want. Is good. 216. 180. I can get 120, I think. Nice. Let's just score up. How'd you do it?
6 times 6 times 3 plus 2.
6 times 6 times 3 plus 2. Yeah. Good. So you'd win that round. But you're getting kids to call out whatever answers they're getting, right? And so that they're just playing around with the numbers and trying to figure out something that's a little bit better, play around with it, and the best person who wins gets a point. You don't have to get, it's different from crypto in that you don't have to get an exact solution. You can play around with it and try to get as close as possible. You roll again, you play again. So something like this, if you got an extra 5 or 10 minutes in your classroom, if you've got something, kids love doing these kind of game type things. Easy to do, you're just rolling and asking them for solutions, but something that's directly designed to get them to play with numbers. They don't play with numbers enough. My mom always says the reason why I'm good at math is when I was 2, she played endless games of war with me. And that's probably true, the reason why I'm good at math. Just because there's intentional, and not that war is playing with numbers, but some kind of associating this, we would invent new games, all these kinds of things. Get creative about finding ways specifically for kids to play with numbers. If you really want some rules to either of those games, I think I've got some rule sheets somewhere that you can have. The other way of doing this, right? I've seen this happen, actually, I watched it happen really well in Mr. Beach's class. Right? Some kind of a non-curricular problem with no real exact solution. Found really effective. For instance, I actually got a text from a friend the other day. Said, all right, I'm at this concert. And he drew me a little picture. He said, I'm at this concert. Here's the stage. And it looks something like this. And there's a line of porta potties along the back. Given a random place in the concert, what's the probability that I should go into the center and then back out, one of the radial lines, versus going out and around? There's no exact solution to this. Right? Well, he didn't give me enough information to do it, but I spent about an hour and a half on it and came up with something relatively creative. All right? Interesting problem. Right? And actually, there was a couple of really fun things about the units of that problem, some of the variables that I assigned to various things that then were related, like, that were ended up being able to relate to one another in cool ways. But something like that designed, you don't want to do this every day necessarily, but every once in a while, bring in something like that designed to just play around with it. There's no exact solution, but all we're doing is playing. All we're doing with messing around. We have to make some assumptions. We have to write some equations. We have to know a few concepts. Right? I have to know some things about circles and how the radius is related to circumference. But really, all I'm doing is playing with the students. I'm messing around, getting them to think about something in a little bit of a not following the formula way, but having to make that creative move, having to make that starting point, having to start thinking about what things matter and what things don't matter and how much do they matter. Actually, the radius of that problem matters not at all. Doesn't matter. Doesn't matter how big your circle is. Really cool, right? Find some ways to incorporate specific ways where you're not looking for anything except for them to play, except for them to try something. Some of the indirect ways are more important, I think, in this scenario. A couple thoughts. Let them play in order to generate the formulas. Let them play before you generate formulas. For instance, a problem like this. Before you taught them linear combination or substitution, throw the problem up there and let them mess around with it for a while. Maybe you might get some answers, right? Let them mess with it. Give them, have someone say, what's the answer going to be? 3 and 8. All right, why do 3 and 8 not work? What would we have to change it? Well, we can make y bigger. We can make x bigger. Why doesn't it work to make y bigger? Well, then you got to deal with that second problem. But actually, what's going to happen here, not just they're going to play with it, what actually happens is that at the end of that playing, you end up with the idea that what we need is a way to take both of those equations and work with them at the same time without losing the information in either one. And guess what substitution and linear combination are? That's what they are, right? They're a way of using both equations at the same time without losing the information in either one. And the way they get that is to play around with it for a while and say, man, it would be really helpful if we had this. And now you're like, boom, formula, or boom, process of doing this. Because that's how it got invented. Someone was messing around with it and say, I know how to do this. I can do this every single time. And let the kids play before you give them the process. Let them play with it for a while. Call it answers. Have them call it answers. Be comfortable with the wrong thing, because every time you say, that's a great idea. Let's just check it out. Oh, it doesn't quite work? Okay, well, how can we change it? These kind of things. Really, really fun things. And guys, I cannot emphasize this enough. That is what's fun about teaching. No one wakes up in the morning and says, I'm really excited to make sure my kids have the quadratic formula down in their notes today. We just don't do that. I'm really excited to have them play around with quadratics until we figure something out together. That's what I'm going to say. Okay, I'm sorry. Next. And related to this. Something like pursue wrong avenues of thought in your classroom. Pursue wrong avenues of thought. When you get an answer that's incorrect, take it and run with it until it becomes really apparent that it's incorrect. And don't do that in a way that the student who gave that answer is going to be uncomfortable, but do it in a way encourage that answer. Say, that's a really good idea. And even at the end, come back and say, well, okay, we saw that it was wrong, but why did you say that? There's a really good idea in there. Something like, I don't know, a couple different examples I thought of here. Throw that problem on the board after you've taught factoring, but before you've taught the quadratic formula or completing the square. They're always going to be, I'm specifically seeking out wrong avenues of thought here, right? They don't have the right avenue of thought. I'm specifically making them give me wrong answers. In order to get the idea of what it means to play around with a quadratic, and what it might mean to solve something like that, and why factoring doesn't work, but also to generate a culture in my classroom where being wrong is okay, just because, not being wrong is okay in that wrong answers, right answers, we don't care about it, but being wrong is part of the way we get to the right answer. I love doing something like, I don't know if you're doing calculus, right? Throw something like this. Right? It's a partial fraction decomposition problem. You can only solve it by partial fraction decomposition. But I guarantee you, students will try U substitution. I guarantee they'll try integration by parts. They'll play around with it for a while. And they'll come to realize that it can't be integration by parts because it's so close to being integration by parts, or it's so close to being a U substitution problem. It's neither of those two things. It's so close. And they're playing with it. They're coming to the realization that I need something new. I need something new. You're okay being wrong. Because someone says, we can do a U substitution here. Great, let's do it. U equals what? Oh, U equals x squared minus 2x minus 3? That sounds right. All right. 2x minus 2. Let's make our substitution and run with it. Take it and go. Run with it. You don't need to shut down wrong answers whenever they're given. Don't shut them down. They are wrong, but take them and go with them. That culture of your classroom will change overnight. Not overnight. Over a long period of time. A long period of very difficult time. Yeah?
Do you ever indicate that that's a form of indirect proof?
What do you mean by that?
Can you point that out?
Yeah. You mean saying something like, sorry, go ahead.
Well, taking that wrong answer and then using that to lead to other things until you come up with a result that's obviously false.
Sure.
Which then you go back to the beginning and say, well, our original premise was that false.
That's exactly right. Yeah. Say, okay, we came to a logical inconsistency, therefore our step at the very beginning can't be right. Is there another step we can do? Yeah, it's the RAA kind of a proof. RAA, reductio ad absurdum. So like, reductio ad, I'm doing that right? Is that right? RAA? Yeah. So you make an assumption, take it to something that you know is going to be false, therefore your assumption, it's called RAA proof or indirect proof. Yeah. Yeah, some mathematicians think RAA proofs are completely wrong. They only like direct proofs. But it's not me. Not me. I'm a big fan. All right. There's a couple other things I was thinking about in here. All right. Discuss strategies and explanations. Right? I love doing this with my students. I call it a 30-second explanation. I've told some of you this. Right? But ask them for a 30-second explanation of a problem. Right? Or let's try one. Let's see. Mr. Wagner, 30-second explanation of a parabola. Go. Done. Nice. Well done. Good. Round of applause, round of applause, round of applause, round of applause. Someone else. 30-second explanation of this problem right here. Tomek, go. Solve it. Whole problem. 30 seconds.
Finding the least denominator of all four of the various fractions, and realizing that the numerator is going to be negative, and since you're adding the denominator to two positive numbers, then it's going to be positive, so the answer has to be negative.
Time. Good. Good. What am I doing when I'm doing that? What did he have to do to give that? What do you have to do? Going over the process in his mind, right? Distilling the important things from the unimportant things. If you have 30 seconds to explain it, you can't say something like, first I made a comment. Right. I'm sure you guys hear this all the time when you ask your students to explain a problem. So 2 over 3, I had to multiply both the numerator and the denominator by 2, which gives me 4 over 6, and 1 over 3, I had to multiply the numerator, and it just bogs your class down. Right? 30-second explanation, like, now you're on the clock, right? You have to distill the important things from the non-important things and hit the essential kind of things. Say, so I noticed that all my denominators had a common denominator of 18, so I multiplied the top and the bottom by 18. I can do that because 18 over 18 is 1. And I can multiply anything I want by 1. 18 cancels out all my denominators, leaves me with several things in the numerators, subtracted and added, and I was good to go. Something like that. 30-second explanation. You have to coach your students on how to do that. They're not going to do that right away, but give them a chance and then say, who can give me a better 30-second explanation of that problem? Who can give me these kind of things, getting them the chance to distill the important parts of what happened in the middle from the unimportant parts. Really good. Talk strategies with them. Related, right? Celebrate different ways to get an answer. Celebrate that. Every system of equations. Celebrate both substitution and linear combination. Have one of your students who's like a substitution guy, and he's going to do substitution every single time. And like, you're my substitution guy, right? How'd substitution work on that problem? Right? You know there's a couple kids who really just love substitution and hate linear combination. And there's other students who really love linear combination. And some problems, right? It's so hard to do linear combination with, or other problems, it's almost impossible to do substitution. You get so many fractions and gross things, right? And so you celebrate both the different ways. You take those papers and you throw them under the document camera and you say, look what this guy did. That's so cool. Your kids are going to start being the ones who want to have their papers under the document camera because, oh, that was cool. That was different. I did it a different way. I thought about it this way. I thought about it this way. I thought about it this way is always really good. Celebrate those kind of things. Just a little bit more up here, maybe. If you haven't played around with some extra credit questions just on an exam, I'm talking about not curricular extra credit questions, but just questions designed to have the kids mess around with them for a while. Like, I don't know, some of the classic math puzzles. If you guys are going to the math puzzles one, you'll probably get some good ideas for some good extra credit questions. Something like this. Draw 4 lines, straight lines that are connected that hit each one of those 9 points. All right. Some of you guys have probably seen this before. Some of you guys maybe haven't, in which case it's a fun one. It's a really fun one. It's very difficult. All right, you think, okay, 4 lines. 1, 2, 3, 4. I missed one. Solution's pretty fun. I'll let that simmer so that some of you guys can work on it for a while. It's a fun one. But things like, even just stuff like, I don't know. Fill in 6 circles so that there are an even number of circles in each row and column. Stuff like this, right? I'm throwing it, give half a point on your test for it so that it doesn't really affect the grade, but let your kids play around with stuff for a while. Let them mess with stuff. Actually matters in terms of number sense is this kind of stuff. This is what more mathematics is. 6 circles, even number in each row and column. Go for it. How many squares are there on a chessboard? How many squares are there on a chessboard? There's 64 1-by-1 squares. Throw it at the end of your test and see what happens, right? Make them play around with it for a while. Yeah, right? Mess with them. Cool. Let's do the last one I think we got, what do we have, 5 minutes? Oh my gosh. I'm not going to nearly get to what I want to get to. It's okay. 3. Let's just do confirmation for just a sec. Again, I think this is an easier one, especially with this indirect portion, the habits of teaching. Habits of teaching, just like at the beginning of every problem, by making a prediction, end every problem by asking whether it makes sense, asking why it makes sense, asking how it compares to your prediction. Right? Is it different? Why is it different? Why is that answer different than we expect? Should that cause us to go and re-look at what we did? Is it different enough that was our prediction right and our answer wrong, or is our answer right and our prediction was off? Why? Those kind of questions. Right. I was going to do that calculus problem and get our answer and say, just have you ask that even this calculus question, why does that answer make sense? Well, it makes sense that we would hit the shore pretty quickly because we can run twice as fast as we can swim. Right? Makes sense that we'd hit that shore pretty quickly. Right? Or, makes sense that the time is about 8-9 hours-ish. I don't know, did anyone end up doing that one while I've been talking? No one? That's good for me. You guys are not bored? Oh, you did? What'd you get for the time it takes?
Actually got the distance.
Oh, yeah. What's the distance? Is it square root of 3?
3 over the square root of 15.
Ah, nice. 3 over root 15. It's a pretty small number.
That's how far it was from directly below.
From directly below, yeah. But asking, right, so indirectly, right, end every problem. End every problem by asking whether or not your answer makes sense. And again, right? Why? Compare it to the beginning. Again, this is something that as mathematicians, we do subconsciously. We end every problem, and like we said at the very beginning, we do this without thinking about it. But our students don't do that, and so we need to make that explicit so that they do think about it until it becomes habit. And it's the easiest thing to incorporate into your teaching. If you want, looking for some number sense ideas, start every problem with a prediction, end every problem with asking why it makes sense. Easiest thing to start incorporating. It doesn't take any extra work on your part. Doesn't take anything fancy, but it gets the kids asking the right kinds of questions. Easy. Maybe the indirect or the direct ways of doing this. I do this directly on homework, actually, which sounds, I don't know if I have time to go into my entire homework policy here, but what I do is the thing that I look for on my homework is for students not to get answers so much as to make observations about their problems. I have been known, and I tell my students this, to give 10s on homework that has no right answers, which I know is not very, you don't want to get in the habit of doing that necessarily. But if a student said something, got stuck on a problem, whatever, maybe your calculus problem, if they got stuck and they said, I got stuck here. This is what they're writing this on the problem. on the problem in their homework. I got stuck here. I tried this, and I got stuck there. I tried this, and I got stuck there. I don't know what to do, but here's what I tried, and here's why it was wrong. And they write that on their problem. I will give that a 10 out of 10 every time, and they know that. When they get stuck, they know. Now, I won't give that right. You can't get that right on the test, right? You can't get that right on a quiz or something like that. You don't get points for that. But on a homework assignment, when I'm looking for them to communicate with me, and looking for them to say, I'll ask questions on homework that say, why does this make sense? And if you can get the right answer but not tell me why it makes sense, you're definitely not going to get full points on it. Right? If you're correcting your homework and if they say, I got this one wrong, I got this one, and they write next to it while they're correcting it. I got this one wrong, Professor Greg, but I know exactly why I went wrong. I went wrong right here. Right? And I'm not going to do that again. These kind of things, on my homework, I directly encourage them to stop and think about their problems and stop and think about, to put a little thing like this after problem 1 and problem 2 and say something like, this is different because, right? I incentivize, 2 is different than 1 because of this. Find ways to incentivize them to make those kind of observations. I do it by specifically crafting my homework and my homework policies in order to encourage that. You may do it a different way. I'm just trying to get students in the habit of not just rushing through the calculation, but figuring out a way to stop, confirm, and review what they're doing. Stopping and confirming and reviewing what they're doing. Saying like, they get to the end of a problem, I know this is wrong because the answer is too big. I know I did this right, but I know something's wrong. I'm not really sure, but it's got to be in one of these couple steps. Something like that, written at the end of a homework assignment, right? That shows me not maybe true understanding or true fluency with the process, but it shows me as a teacher that they are thinking about the problem and not just using it as another thing to complete. What we really want to do is we want to generate thought. We want to generate confidence and habits of doing some of these kind of things to do number sense. Okay. It's not easy because your students will be bad at literally all of these things the first several times that you do them, the first year that you do them, the first months that you do them. They'll be bad at all of them because they haven't been trained in any of these things. They're so worth trying to start doing in your classroom and to start thinking about some other ways you can do it. If you have other thoughts about these, I was hoping to leave like half an hour for other thoughts about this. Obviously, that didn't happen. I'd love to hear some of your other thoughts, but not now because you guys are tired of hearing me talk and want to go grab some coffee. Thank you all.
Thank you.